Okay, so in the simulation, you can kind of just mess with different aspects of a gas to see how it affects other aspects. So I'm gonna pump some gas in there. So remember that fart? It starts on one side of the room and it spreads. This is how gases work. They expand to fill their container. So let's just kind of refresh our memories about how gases work. So what I'm gonna do first is I'm gonna heat up the gas. So if I heat up the gas, what do you guys think will happen to the pressure? Will the pressure go up or will it go down? Yeah, up, right? Because if I heat up the gas, what happens is you start making the gas molecules move faster. And as you guys can see, the pressure will slowly go up because if they move faster, they're gonna hit the walls faster. And then vice versa. If we cool it down, ooh, a little ice comes out. If you cool it down, the molecules will move slower and then that'll make the pressure go down, okay? So that's just a little fun little simulation that you guys can use to kind of visualize what's going on with different gases. If you change different aspects of the gas, I think you can also make the container smaller. And so if you make the container smaller, that'll change the pressure and the temperature and things like that as well. So just a little handy simulation you guys can use to make sure that you're understanding how gases operate. Okay, any questions about that? Hopefully it's kind of helpful. All right, if not, let's jump into the lesson for today. So last time we talked about those 5 gas laws, but today we're going to be talking about probably the most important gas law, and it's called the ideal gas law or ideal gas equation. Okay, so that's what we're going to be talking about today. This section is called the ideal gas law or the ideal gas equation. Okay, I'll probably call it the gas law. Okay, so one thing we do need to clarify is that when we use this equation, we're assuming the gas we're looking at is an ideal gas. Okay, it's not real, it's hypothetical. And in an ideal gas, the molecules of an ideal gas do not interact with each other. So when we have, in reality, gas molecules will bump into each other. They won't just bump into the walls of their container. But in an ideal gas, we assume that they don't interact with one another, okay? And this is important because some gases can interact with each other and react with each other. There's electronic forces that do affect how they interact with each other. We don't assume any of those things happen in an ideal gas, okay? And then in an ideal gas, the combined volume of the molecules is smaller than the volume of the gas occupied, okay? So when we have a gas, right, we have a big container, but we only have a few molecules in there, right? So if I actually put the molecules in one spot, it would barely take up any space. But in an ideal gas, we just assume that the molecules don't take up any space at all, okay? So just know that in an ideal gas, this isn't how real gases work, but for the purposes of this class, we'll just be assuming these two things, okay? So the ideal gas law isn't perfect. It's not going to perfectly describe gases, but it's good enough. Okay, there's going to be a little bit of error, but it's good enough, and that's why we use it. Okay. All right. Any questions about the presuppositions we have about the gas law before we get into using it? Okay. All right. So this is the ideal gas law equation. Make sure you guys write this down. Okay. You're going to need to know it. I would encourage you guys to memorize it just because we'll be using it so much. You guys might end up memorizing it. But it's PV equals nRT. And we'll talk about what those variables stand for. But just write that down somewhere on your paper. Okay. PV equals nRT. Now, these, dude, this happens every time. How do I never know when announcements start? Good morning, Kermit. That, guys. Okay, so for the ideal gas law, you guys see it up there. Hopefully you guys were able to write that down during the announcements. But we'll talk about what all the variables mean, and then we'll do a couple practice problems because that's probably the best way to understand it. Okay, so in an ideal gas law, basically what this gas law tells us is that if I have a container of a gas, right, containing gas molecules, if I know if I want to know one of the variables, so let's say that I want to know the pressure of the gas. If I know the volume, right, N, which is how many moles there are, and the temperature of the gas, I can calculate the one that I'm missing. So basically it tells you that if you want to find out one of these properties of a gas, by knowing 3 of the other properties, you can figure out the property that you want to find out. Does that make sense? Okay, so these are pretty easy. P, V, N, and T is just pressure, volume. N stands for moles, and then T is the temperature, but just make sure you guys know that temperature has to be in Kelvin, okay? All right, well, there is one variable that is kind of weird, and it's R, okay? R is called the gas constant, okay? And the gas constant is basically a number that is constant. It doesn't really change. We're always going to use the same value for R. Okay, but the problem with R is that the number and the value variables you're going to use for R, it's going to depend on how you measure the other variables. Because remember how we talked about last time, we can measure pressure in a variety of ways, right? We can measure it in atmospheres, we can measure it in torr, we can measure it in PSI, right? You guys remember that? Same thing with volume. You can measure it in milliliters, liters, milliliters, and centimeters cubed. Moles is always going to be moles. Temperature always has to be Kelvin. But depending on how you measure pressure and volume, you might have to use a different number for R, for the gas constant, okay? And so just make sure you guys are careful about the variables. So I'm going to move down. And here I have a little table where it tells you what R can be based on the way that you measure the other variables. Okay, so if I use liters for volume and ATM for pressure, I'll use the number 0.08206. Okay, if I use joules, moles, and Kelvin, then I'm going to use 8.314. So just make sure that you guys are careful of how I give you the numbers. If the numbers that you are given that from me or the AP test, just make sure you guys are very wary about which units of measurement are given to you, because that will determine what value of R you need to use, okay? So just keep that in mind. These will be provided for you, but you'll usually, not like 99% of the time, you'll be using this one right here, okay? But just be careful of the units, okay? All right, so with that being said, let's use our ideal gas law for the first problems. So it's PV equals nRT. Okay, it wants you to calculate the volume of a gas in liters if 9.5 moles has a pressure of 0.88 atm and a temperature of -15 degrees Celsius. Again, if you guys feel confident doing this on your own, you can just kind of zone me out for a sec and try it out. But I'm going to go through it step by step so that we're all on the same page. Okay, so the first thing we want to do is we want to figure out what variables do we have. Okay, so let's start with 9.5 moles. So which of these 5 variables does 9.5 moles represent? N, yeah, good. N, so our N is going to be 9.5 moles. Okay, it tells us our pressure is 0.88 atm. So for pressure, we can just write 0.88 atm. That one's pretty easy. Okay, and then our temperature is -15 degrees Celsius, okay? So I can just plug these numbers into the equation, right? No, why not? Yeah, the temperature, it's in Celsius. Remember, temperature always has to be in Kelvin. So what we're gonna do is we're gonna add 273.15, and that will get us our temperature. Now remember, this is negative, so we're not going to be going up 15 degrees. We're going to be going down 15 degrees. Okay, so I'm going to give you guys a minute. Try to finish up this problem on your own. Try to figure out which variable, which number for R you should be using. I'll give you guys a minute to figure that out, and then after that, we will finish up this problem together. Okay, so you should be plugging in the variables and then figuring out what value we should be using for R. Maybe another 30 seconds to finish that up. Alrighty, guys. So if you're finishing up, feel free to finish up, and then you can just check your answers at the end. Okay, so let's plug in our numbers. So for this problem, it looks like we're looking for volume, right? So we need to solve for V. So if I rearrange this equation, what I can do is I can divide by P on both sides, and that way it'll isolate the V. That way I can just have this nice fraction that I can solve for to get volume. Okay, if you guys just plugged it in the normal way and then just solve for V, that's fine. But I like to kind of rearrange my equations. That way I can just plug in the numbers one time and then I'll be all done. Okay. So if we rearrange the ideal gas law, it will be the same thing as volume is moles R and temperature over P. Okay, so I'm just going to plug in my numbers from here. Okay, so my moles is 9.5, so I'm going to plug in 19.5 moles. Okay, now we need to figure out R. Okay, so if you guys notice, let's look at our units. We have moles, we have ATM for pressure, and we have Kelvin. So if we look for the units that are present, if you look at the first one, you're going to have moles, atmospheres, and you have Kelvin. So this is the one that we're going to be using, which means that when we solve for volume, we're going to have the volume in liters because that's the measurement for volume that this value gives us. So we're going to plug in 0.08206. And if you want to actually write the units, it'll be liters times ATM over moles times Kelvin. Okay. And then lastly, we can put in our temperature, which is 258.15 Kelvin. And then we're going to divide by the atmospheres, which is 0.88 ATM. All right, so I'm going to start canceling out some units so it looks a little bit pretty before we plug it into the calculator. But do you guys have any questions how we plug that in or why we're using that value for volume or for the gas constant? Okay, so if you guys start canceling out the units, you'll see why we want to use that value. So if you notice, we have moles right here. And then there's a moles on the bottom of this fraction. So if we have something on top and one on the bottom, they can cancel out. We have ATM on the top of this fraction, ATM on the bottom, so these can cancel out. And then we have Kelvin on the bottom here and Kelvin here, so the Kelvin cancels out. And then the only unit we're left with is liters, which is a measurement for volume. So that's the reason why we would use that value for R in this situation, okay? All right, so let's plug and chug into the calculator and we'll be done. So we do 9.5 times 0.08206 times 258.15, and then we're going to divide that by 0.88. And then there you go. You have the volume of your gas. The volume of your gas will be 228.689 liters. All right, and that's your answer. So the ideal gas law, and I think just every law in this class is just basically simple algebra. We just plug in numbers and then we just make sure the units all cancel out, and that's what we should get. Okay. Any questions? Pretty easy. All right. So I'm going to have you guys try 5.7 on your own. I'm going to leave this up here for like maybe 10 more seconds for people to finish copying down. But I want you to try 5.7 on your own. Now, this one is going to require you to do one extra step because instead of looking for something in the gas law, you're asked to find the number of gas molecules inside of this container. Okay. So if you guys remember, you're going to have to use a different, you're going to have to use one conversion factor, and it's that 1 mole is equal to 6.02 times 10 to the 23rd molecules. Okay, so you will need that conversion factor and you'll need the ideal gas law. So I'll give you guys maybe about 2 minutes. You can work with the person next to you but just use the variables that you have to solve for the number of gas molecules. Again, you'll need to use the ideal gas law, and you'll have to use one conversion in order to find the correct answer. Okay, so I'll give you guys some time to do that. All right, I'll give you guys maybe 30 more seconds to try that out. Alrighty, guys. So if you guys are finishing up, feel free to finish up on your own, but I'm going to start going over it for the sake of time, and so that we all have the right answer. Okay. So in this problem, again, you're not looking for anything in the ideal gas equation. You are looking for the number of gas molecules, which means that you're going to have to use this equation to find something which you will convert into gas molecules. So just based on what we learned, which one of the variables that we have can be turned into gas molecules? Yeah, N. Dude, you guys are so good at this. Yeah, you can turn moles into gas molecules by using this conversion. So in this problem, we are going to be solving for N, okay? So if I rearrange this equation, again, you don't have to do it this way, but I like to do it this way. If you rearrange the equation, you will get N is equal to PV divided by RT, okay, because I can just divide by RT on both sides. Now, I'm going to start by plugging in my numbers based on what I'm given, okay? So if we take a look at this problem, what is our value for pressure? Yeah, 740 torr. That's going to be another way we measure pressure. So 740 torr. Okay, that's our pressure. Now let's look at volume. Volume's pretty easy. It's just right there, 4 liters. Okay, and then we're going to divide that by R. So we got to pick our R value. Okay, so if you guys notice, we have torr and liters. And so if you look down here, we have torr and liters. And so we can use the value 62.36 for our value. Okay, and if we want to write the units, it's going to be liters torr divided by mole Kelvin. Okay. And then for our temperature, we have 298. If we add 273.15 to it, that'll give us 298. I solved it on my own, but 298 Kelvin. Okay, it's 25 plus 273. Okay, before we go on, let's just make sure our units all cancel out. We have a torr on the top of the fraction and on the bottom, so they cancel out. We have liters on top of the fraction at the bottom, so they cancel out. We have Kelvin down here and a Kelvin even underneath that, so that those cancel out. And it looks like we have moles on the bottom of a fraction, but if you guys know, if you have something on the bottom of, if you have a fraction on the bottom of a fraction, whatever is on the bottom just goes to the top. So that means that this is going to give us moles for our units. So that works out, okay? Okay, now we can just plug and chug into the calculator, and that'll give us our value for N. And so let me just pull this up. So we'll do 740 times 4 divided by 62.36, and then divided again by 298.15. That'll give us 0.159. Okay, so we'll get 0.159 moles for our gases. Okay, so we have 0.159 moles of the gas. Now we're not done yet because we're not looking for moles, we're looking for molecules. So from here, very simple, we just use the 0.159 moles. We do a simple conversion. We put 1 mole on the bottom. We put 6.02 times 10 to the 23rd on the top. The moles will cancel out, and then we can just solve from there. Okay, so if you guys remember, we just need to do the math for the regular numbers first. So we multiply what we have by 6.02, and then that'll give us 0.958. So we have 0.958, and then we just move the scientific notation, which is times 10 to the 23rd. But remember, we need to move the decimal 1 time to the left, so there's only 1 number in front of it. If we move the decimal to the left, the value is going to go down for the exponent. So we'll have 9.58 times 10 to the 22nd gas molecules. Okay, so if you guys were able to get that on your own, good job. If not, that's all good. I know this is new, and we do need a little bit more practice with it. Okay, any questions on the steps that we took to solve this problem? I know there's a lot of algebra involved. Sometimes I can't tell if you guys are good or just too tired to care. Both, okay, for sure. Is it because I haven't made any fart jokes yet? Yeah, sorry. Hey, next time for our lab, we'll have you fart in a balloon and then we'll calculate the number of gas molecules in there. No, I'm just kidding. That's really gross. But I have tried that before. But yeah, I couldn't produce enough to fill up the balloon though. That's the problem. There is some methane in there, but the thing that makes it smell is the sulfur. So I don't know if you guys know this, but if you eat a lot of egg yolk and then you fart, dude, it's crazy. Like it's like, yeah, it's amazing. All right, anyway, any questions? Okay. All right, let's move on. We're gonna jump down to 5.9. Okay, so 5.9, here you don't have that much information given to you in the problem. It tells you to find the volume of 1 mole of an ideal gas at STP, okay, standard temperature and pressure. And so to solve this problem, you'll have to go to the top of your notes to find out what STP is. Okay, you're gonna be using the ideal gas equation, again, PV equals nRT. And so I want you guys to try solving this on your own. I'm gonna give you guys 3 minutes to do this. And I want you guys to figure out, hey, what is the volume of 1 mole of gas at STP, standard temperature and pressure? If you wanna see what standard temperature and pressure is, you're gonna have to go basically to the top of the notes. There's a part where it tells you what standard temperature and pressure is, okay? Take about 3 minutes, try solving that out. You're looking for volume, and just make sure that you guys use the correct value for R. Okay, you guys about 3 minutes. The R value? Yeah. I would recommend you memorize 0.082, but you're not gonna have to memorize the other ones, because if you're able to convert between the pressures and the volume, you can always get it back to 0.082. Yeah. But it's one of those things you'll kind of just memorize on your own. Yeah. So hopefully you're able to figure out that in STP, the pressure is 1 atmosphere and the temperature is 273.15 Kelvin. So if you guys use those values, you should be able to solve it. So I'll give you guys maybe another 45 seconds to fill that out. And then we will go over it together before moving on. Alrighty, guys, so I have the equation up here, and let's just make sure we have the correct R value. So if we're solving for volume, we'll use 1 mole for N, we'll use 273.15 for the Kelvin, and we'll use 1 atm for the pressure. Now, since we have atmospheres, Kelvin, and moles, for the R value, what we're gonna do is we're just gonna go up to that table real quick, and you should see that we're gonna use 0.082. I'm gonna round it up to 1, just so that we don't have to write so many numbers. And this is going to be our R value, okay, because those are the ones that we have. Okay, so for our R value, we'll just plug in 0.0821. Okay, if you did the 8206, that's fine. You'll basically get the same answer. Okay, and then from here, we just need to calculate 0.0821 times 273.15, and that will give you your value. Actually, sorry for this one. Let's do 0.06. Sorry. So 0.08206 times 273.15. Yeah. So you should have gotten an answer of about 22.415. Okay. Did everyone get that, leaders? Okay, so what this tells us is that when we have 1 mole of a gas at STP, it will take up about 22.415 liters of space. Okay, and so we're going to use this value right here, and I want you guys to go to 5.10. So 5.10, we have a bunch of different gases, and they have different volumes, and I want you molar volumes, and I want you guys to use the value that we just got to figure out which one of these 6 gases is most similar to an ideal gas. Okay, so this table shows us the different types of molecules, different types of gases, and it tells us how much 1 mole of them, how much volume 1 mole of them takes up. This is real life data, and I want you guys to figure out which one of these gases is most similar to an ideal gas. Okay, so take about 30 seconds. Look at the chart and try to figure that out. Which one of these is most similar to an ideal gas? Alrighty, guys. So let's go over this. If you guys are a little confused, basically all we need to do is take our answer from the previous example. We said that 1 mole of an ideal gas at STP is going to take up 22.41 liters of space. Okay, so we're going to go through this and just based on what you guys see, which one of these is most similar to an ideal gas? Helium. Yeah, helium. Good. Okay, so helium is most similar to an ideal gas because it has a number that's the closest to 22.414. Okay, now this is actually kind of significant because remember the assumptions that we made about the ideal gas. We said that we assume that the gas molecules take up no space, right? We don't assume the space of the actual molecules. Well, if you guys notice, helium is very, very small. Cl2 has a molar mass of what, like 71. Carbon dioxide has one of 44. Ammonia has one of 17. Nitrogen is 28. Helium is 2. Okay, hydrogen is also 2. Now, if you guys remember, the other assumption is that the gas molecules, they don't interact with one another. So there's no interaction. And if you guys know, helium is a noble gas. And noble gases, they're kind of happy the way they are. They don't like to interact with other things. And so that's why helium, it makes sense that it is most similar to an ideal gas. Okay? Any questions about that? All righty. Okay, let's move on to the next topic. Next topic, we're going to be talking about density. We're going to go through this one really quickly. Not much to say about it, but we can determine the density of different gases based on the ideal gas law. Okay, so we usually measure density of gases in grams per liter or grams per milliliter. And since the volume of a gas can change based on the pressure and the temperature, the density can change because the volume can change as well. Okay, so this is a simple equation that we can use. And so I just want you guys to take maybe about a minute, use that equation to figure out the density of radon at 800 torr and 100 degrees Celsius. Okay. Oh, sorry, I forgot to mention something. This right here is molar mass. It's pretty important. Okay, that little symbol, that U symbol, mu, it's called mu, and mu is molar mass. Sorry about that, guys. Kind of impossible to solve that without it. Alrighty, guys. So if you guys are finishing up, feel free to do that on your own, but I'm going to take it step by step just so that we're all on the same page. Okay, so for our equation, we're going to use this one right here because we have pressure and temperature. This is pressure, this is temperature. And so we just need to plug in the numbers for radon's density, okay? So on the top, we're gonna plug in pressure. Our pressure is 800 torr, so I'm gonna plug in 800 torr on the top. Okay, we're gonna look at the molar mass of radon. You should have gotten 222 grams per mole. Okay, and then for our R value, if you guys go up to the table, we're gonna be looking for one that has torr in it. So if we go to the top, you guys should see the one with torr is 62.36. So we're gonna be doing 62.36. And then for our temperature, it's 100 degrees Celsius, so we need to add 273 to it. So 373.15 Kelvin is going to be our temperature. So 373.15 Kelvin. Okay, so we're gonna start solving this now. And so what we're gonna do is we're gonna plug and chug into the calculator. So we have 800 on the top, multiplied by 222. We're going to divide that by 62.36, divided by 373.15. And then for our number, we're going to get 7.3632. Okay, now we need to figure out what the units are. Now it says that it can be grams per liter or grams per milliliter. But if you guys take a look at this value of, what is it? For R, the gas constant, you should see that it has liters inside of it. So the final answer is going to be grams per liter, okay? So there you go. That is going to be your answer for the density of radon at 800 torr and 100 degrees Celsius. Okay. Any questions? All right, so we're gonna take a 5-minute break just so you guys can kind of chill out before we finish up the lecture for today. So take about 5 minutes. You can just relax a bit. If you have any questions, you can let me know, or you can finish copying that down. So take about 5 minutes to relax. All righty, guys, let's bring it all back together, and then we'll move on to the next topic. We're gonna skip the next couple problems, and we're gonna go to section 4. Okay, we're gonna be talking about something called partial pressure. So up until this point, we've been looking at gases when they're just by themselves, okay? But now we're going to be looking at containers that have multiple gases inside of them, because that's more similar to what it's like in real life, right? It's very difficult for us, at least in this class, to have a container with just one type of gas in it, because the air around us is a mixture. And so all of the different gases that are around us, they have different pressures, right? And so there's a law called Dalton's law of partial pressures, and it basically tells us that the total pressure of a gas mixture is equivalent to the sum of the pressures of each individual gas. So this is the equation right here. But basically what this is telling us is that, hey, if oxygen has a certain pressure and nitrogen has a certain pressure, and you mix those two gases together, their pressure is going to be the total or the sum of the combined gases. So if oxygen is 159, nitrogen is 593, the total pressure when you mix them together is going to be 752. Okay? And that's pretty much it. Okay, so that seems really easy, but we can do a lot of different things with that equation. Okay, and it can kind of go into a lot of funky scenarios. Okay, but before we move on, do you guys have any questions about how that equation works? If you want to find the total pressure, you just need to add, excuse me, you just need to add the pressures of the constituent gases. Okay. All right, so let's use that in a problem. So we have 5.14. We'll do this together, and then we will do some other practice problems going forward. So it says here we have a mixture of 6 grams of oxygen gas and 9 grams of methane. Okay, and we put it in a 15-liter container at 0 degrees Celsius. Okay, it wants us to find the partial pressure of each gas and the total pressure of the gas mixture. So in this question, it's asking us for the total pressure. Okay, I'm going to write that as P tot. Okay. It also wants us to find the partial pressure of each gas. So the pressure of oxygen and the pressure of methane. Okay, now we just learned, based on Dalton's law of partial pressure, that the total pressure is equal to the pressure of the gases it's made out of. So that means if we can find total pressure, we can find the pressure of oxygen and methane, or vice versa, okay? So this is the equation that we can kind of take out of there, and we're looking for all three of these values. Oh, okay. All right, so let's take the values that we have and try to solve that out. Okay, now we have a container and it's filled with oxygen gas and methane gas. The container is 15 liters and the temperature is 0 degrees Celsius, so that's 273.15 Kelvin. Now we won't be able to find the partial pressures immediately because we don't have information about the individual gases. We have information about the entire mixture. And so what we're going to be doing is we're going to be finding this one first. We're going to be finding total pressure. So in order to find total pressure, what we have to do is we need to use the ideal gas law, PV equals nRT. Okay. So we have volume right here. We have 15. We have temperature right here, and we're looking for pressure. So we have volume, we have temperature, and we're looking for pressure. And obviously we can find R because it's a constant. So if we look at this, it means that we need to figure out what moles are, right? We need to find N in order to figure out what the pressure is. Okay, luckily for us, in the problem, it tells you how much of each gas you have. It tells us that inside the container, we put in 6 grams of oxygen gas and 9 grams of methane. Okay, and so there's 6 grams of oxygen in here, 9 grams of methane in there. Okay. All we need to do now is turn the grams into moles, and then if we add them together, that'll tell us how many moles there are in total inside of that container. Does that make sense? Right? Because if we put in grams, right, we can just convert the numbers we have for grams into moles. So I'm going to do the one for oxygen. I want you guys to do the one for methane. Just figure out how many moles of methane there are, and then we'll just come back together and add them together to get our value for N, okay? So take a second. I want you guys to find the molar mass of methane and then convert it into moles. All right, you guys, so hopefully you were able to get moles of methane. The molar mass is 16. So what did you guys get for the moles of methane? Yeah, perfect. 0.5, and then I'll go 6.3. Okay, so this calculation basically just tells us if I put 6 grams of oxygen, 9 grams of methane in here, it's the same thing as putting 0.188 moles of oxygen and 0.563 moles of methane. Okay, and so if we want to find the total number of moles of gas inside this container, all we need to do is add that up. So our total moles will be 0.751. So our value for N is going to be 0.751. Okay, so now we can solve for the total pressure. If I rearrange the equation, I could put volume on the bottom. Okay, now I'm going to plug in my moles first. So I'm going to put in 0.751 moles. Okay, for our R value, depends what we want to find the pressure in. I'm going to find the pressure in ATM, so I'm going to put 0.0821. And then for the temperature, we'll put 273.15 Kelvin. And then the volume of this container is going to be 15. Okay, so we're going to just solve this out. We got 0.751 times 0.0821 times 273.15. And then we're going to divide that by 15. And that is going to give us a total pressure. This is pressure of the entire container is going to be 1.123 atmospheres. So this is the total pressure. Okay. Any questions? Easy peasy? Okay. So make sure you guys have this written down because we're going to do part 2 now. We're going to find the pressure of oxygen and the pressure of methane. Now, we don't need to change up very many things because we're going to be using this ideal gas law again. Okay, but this time we're just going to be using a different number for the moles, right? Because inside of this container, we're going to have the same for oxygen and methane. It's going to still take up 15 liters of space because gases spread out, right? It's still going to be 273.15 degrees or Kelvin. And so all we need to do is change up the value of N based on how many moles of oxygen we have and how many moles of methane we have. So if we want to find not the total pressure, but if we want to find the pressure of just oxygen, all we need to do is we just need to change the number of moles from total moles to moles of oxygen. So 0.188. Okay, so just plug that in. Everything else stays the same, and that'll let you calculate for the moles of or the pressure of oxygen. Does that make sense? Okay, so take a second to solve that out. If you think you can find methane too, you can do that as well. Okay, and there's an easy way to do this and a hard way to do this for the second partial pressure. Alrighty, guys, so I'm going to start calculating. So very simple. For the pressure of oxygen, we just put in the moles of oxygen, which is 0.188. We multiply that with 0.0821. Oop, to my fat fingers. Okay, times 273.15, and then we'll divide that by 15. And so for the partial pressure of oxygen, you should get 0.8 or 0.281 atmospheres. Sorry, guys, I can't read. Okay, everyone get that? Okay. All right. Now we can do the same thing for methane if we wanted to. We can just change this into 0.563, but that's kind of annoying. But if you guys remember, if we have the pressure of oxygen and the total pressure, we can calculate for the pressure of methane just by subtracting. So we can get the total pressure, which is 1.123 minus 0.281, and that will give us the pressure of methane. All we did was we subtracted the total pressure and the pressure of O2. And that's going to be our 3 values for this problem. And if you want to check your work, you can add the pressure of oxygen, pressure of methane, and that'll give you total pressure. Okay. Alrighty, any questions about that? Okay, so I'm gonna leave this up here for another second, but I want you guys to, if you guys have it up, to go to 5.15. That's the next problem, and this is gonna be the last one that we go over. I want to spend a lot of time on this one, because this is a problem that shows up very frequently on the AP test, and it requires you to conceptualize a lot of different things. We're gonna be taking ideal gas law. We're gonna be taking Dalton's law of partial pressures, and we're gonna be using them and kind of manipulating them a lot based on this situation. So let's go down to 5.15, and that's going to be the last problem that we work on. Okay, so we're going to take a look at this image, and I'm going to explain the image to you guys just so you know what's going on. Okay, so on the left side of the container, it's only nitrogen gas. Okay, and so we have a valve right here. And so if it's blocking the gases from mixing with one another, okay, on one side we have nitrogen gas, and these are the properties for the nitrogen gas. And then on the other side we have oxygen gas, and we have the properties for oxygen gas. So in the beginning, initially, they're separate and they have their own separate properties, okay? So on this side, it's 2 liters, 1 atm, 25 degrees Celsius. And on this side, it's 3 liters, 2 atm, and 25 degrees Celsius. Okay, so the pressures are different and the volume is different. Okay, so in this problem, these type of problems, what they're saying is the valve gets opened and the gases mix, right? So the nitrogen in here is going to, some of it's going to go to this side, some of the oxygen is going to go to this side, and they're going to mix with one another, and they're going to take up the entire container, okay? Okay, so it's asking us now, how does the volume occupied by the nitrogen gas change? Okay, so let's take a look at this. So what was the initial volume of nitrogen? Yeah, 2 liters. Nitrogen initially had a volume of 2 liters. Okay, but what's the final volume of nitrogen after the valve is opened? Yeah, 5 liters. Okay, the reason why is because in the beginning, nitrogen's only on this side. This side has a volume of 2 liters. Okay, but when you change or when you open it, the volume is going to change because nitrogen is able to go to this side now and start expanding to the right side. And if it expands to the right side, it's no longer going to be 2. You need to add up the total volume. And so now it's asking us, so we found the volume occupied by nitrogen, it's going to be 5 liters. Now it's asking us, what is the partial pressure of nitrogen after mixing? Okay, so now we're looking for the pressure of nitrogen after it's mixed. So we're looking for the final pressure of oxygen. So final pressure of nitrogen after you mix it is what we're looking for. Okay, so we have the initial volume, we have the final volume, and we're looking for the final pressure. So what we're going to have to do is we're going to have to use one of our old gas laws from the very beginning to find the final pressure. Okay, I want you guys to go back to the very top and take about 30 seconds. I want you guys to see, hey, which gas law should we be using to find the final partial pressure of nitrogen after it's mixed? Okay, so take about 30 seconds. I want you guys to go to the very top of your notes. It's going to be one of the original gas laws that we learned about. Okay, so take a second to look that up. Then after that, we'll try finishing this up together. Alrighty, guys. Anyone want to take a shot at it? Which gas law we should use to solve this problem? Yeah, Boyle's law. Wow, I'm so impressed. Okay, it's going to be Boyle's law because Boyle's law is P1 V1 equals P2 V2. And so if you guys notice, we have V1 right here. We have V2 right here. It's how the volume changes. And if you guys, we're looking for the final pressure. And if you guys notice, look at that. We have the initial pressure. We have P1. P1 was 1 atm. And so since we have P1, V1, and V2, we can solve for P2, okay, which is the final partial pressure of nitrogen. Okay, so I'll give you guys another minute now. You guys can plug and chug into the equation, and I want you guys to calculate for P2, which is the final pressure of nitrogen. Maybe another 20 seconds or so. Alrighty, guys. So if you guys plug in the values for P1, we're just gonna put, ooh, that's ugly. We're gonna plug in 1 atmosphere. The initial volume was 2 liters, so we're gonna multiply that by 2 liters. And then for the final volume, it's gonna be 5 liters. So liters can cancel out, and so all we need to do is 2 divided by 5 on your calculator, and that should give you 0.4 atmospheres. Everyone got that? Okay, cool. So the partial pressure of nitrogen after you mix it is going to be 0.4 atmospheres. So the point of this problem is that the math is not too bad. It's just a simple 4-number algebra problem. But the thing is, the hard part is conceptualizing what's actually going on. So this is a very common problem on the AP test. And so just make sure that you guys have this in the back of your pocket, that you guys have this understood. If you want to put a star next to it, just so that you guys know this might show up, be a good idea to do that. Okay. Okay, so with that being said, I want you guys to take about 2 minutes and try to answer part B. So we found the partial pressure for nitrogen. I want you guys now to find the partial pressure of oxygen on your own. Okay? Similar process to what we just did. And then after that, if you can, you guys can find the total pressure of the gas mixture. Okay, so for that one, you're gonna have to use the partial pressure law, but try to figure it out. You can work with the person next to you, see if they got some good ideas, and then after that, we'll go over this, and then we'll be all done for the day. Alrighty, guys. So let's finish this up, and then you guys will be done for the day. All right. So we have we're looking for the partial pressure of oxygen in this problem. Okay, so it's basically the same thing we did for nitrogen, but we just need to make sure we figure out the correct variables. Okay, so let's look at oxygen now instead of nitrogen. Okay, so what was oxygen's initial pressure? 2. Yeah, it's 2 atm. That's what oxygen started off with. So we're just gonna plug in 2 atm. What was the initial volume? 3. Okay, 3 liters. And then obviously the total volume or the final volume is going to be the same. It's going to be 5 liters. Okay, so we have our equation. So you just need to do 2 times 3, which is 6, divided by 5, which I'm not going to do in my head. So 6 divided by 5 is going to give you 1.2. Should have got that one. Okay, 1.2. So our partial pressure for oxygen is going to be 1.2 atm. Okay, so the partial pressure for oxygen is 1.2 atm. Okay, pretty simple. And then for the total pressure, all we need to do is add them together. So 0.4 plus 1.2. So the total pressure is going to be equal to 1.6 atm. Okay, so if you guys got that, good work. Hopefully that's not too bad. But again, that is a common question on the AP test. Just make sure you guys have that in your back pocket. Okay. And that's going to be it for today. Do you guys have any questions? Okay, so I know that we have some time left over, so I'll let you guys work on homework 5A. Again, it's going to be due next week. So if you guys want to get a head start on that, you can. If you guys want to ask me any questions about that, you guys can as well. But I'll give you guys the rest of the class period to work on 5A. Yeah, what's up?